Welcome everybody to the Google Federated Learning and Analytics Workshop for 2022. We've been planning this for a long time, so it's delightful that the first day is here. Can we go to the next slide, please? Yeah, I'm Sean Augenstein. I'm a research scientist here at Google. Next slide, please. You've been probably interacting a lot with myself and also with Zachary Charles, who is, maybe Zach, you can wave, who is the co-organizer of this year's workshop. And yeah, we're delighted. Thank you all for putting up with many email blasts, etc. And also, we've been supported in organizing this conference by an amazing set of folks at Google from the University Relations and Events teams. So big thanks to all of them. Yeah, and I'm just going to go through maybe 2 minutes of kind of introductory logistics, and then we will move on to Brendan McMahon from Google, who's our first speaker. So if you can go to the next slide, please. So the goals of this workshop, I think we've had many folks here who have attended previous iterations of this in previous years. We really are all about pushing the forefront of what's possible in federated learning and federated analytics and provable privacy. And in particular, I wanted to emphasize one goal that I think is important, certainly for myself and Zachary this year, and that is establishing collaborations and partnerships. Like, I think we began planning this in the spring. We really envisioned that we would like this to be a place that new research endeavors kind of begin, and not just, end in terms of being a place to present, but really we hope that new connections are forged and new ideas come out of this. So, some program highlights. We'll have some keynotes today and tomorrow. We'll have 2 interesting panel discussions, one today and one tomorrow. And then the other item that's part of the program are mini workshops. And this in particular is something that Zach and I are excited about. If we can go to the next slide. These mini workshops, so in previous years, we've done breakout sessions, which we all found fruitful. And so this year we decided to basically take the breakout sessions and beef them up a little bit, make them longer. So now we have today and tomorrow, on each day, we have 4 parallel, what we're calling mini workshops. And in those mini workshops, they're each 2 hours. There will be part of it devoted to the time. Part of the time will be devoted to a number of short talks. And then part of it will be an open conversation on the particular topic. So we really hope that those are fruitful forums for connections and interesting exchange of ideas. So with that, I'd like to introduce Brendan McMahon of Google as a research scientist here at Google, where he leads efforts on decentralized and privacy-preserving machine learning. His team pioneered the concept of FL, and they continue to push the boundaries of what's possible with working with decentralized data using privacy-preserving techniques. He's previously worked on online learning, large-scale convex optimization, and reinforcement learning, and he has a Ph.D. from Carnegie Mellon. And so with that, Brendan, I'll hand it over to you to talk about federated learning analytics at Google.
Thanks for the intro, Sean. I think at this point, we all actually have a pretty good understanding of FL and its different flavors, as well as the constraints and challenges that the setting entails. And Google continues to deploy federated learning in an increasing array of apps and services. I've highlighted a few here that we've talked about publicly. So rather than talking about the basics, I want to use this talk to highlight a few recent milestones for federated learning and analytics at Google, and hopefully highlight a few interesting open research questions along the way. And the first place I'd like to start is diving into federated learning and privacy in a little bit of detail. One of the biggest observations I think we've had, and I continue to gain new appreciation for, is how multifaceted privacy is as a concept. And this can be a challenge when talking about privacy, because different people can mean different things when they talk about something being private or non-private. In fact, I think we really tried to stay away from kind of treating privacy as a binary concept. And instead, we're trying to at least internally, we've converged on some principles that help separate some of the different concerns with privacy and facilitate a nuanced discussion. So I think these might be useful to go through and kind of facilitating that kind of conversation during this workshop. So I want to start with 4 privacy principles that we found really useful. And again, I want to emphasize the goal of these principles isn't to set a bar for what is private or isn't private. Rather, we found it useful to think about these as kind of independent axes that you can use to evaluate a complete system in different dimensions. So the first principle here is probably the most important, and it's really about the user experience of privacy. Users should have transparency and use-centric control of what data is used, what purpose it is used for, and how it is processed. The middle two principles are, I would say, two different aspects of how a system can actually implement privacy, and I'll dive more into those in the next couple of slides. And then the fourth principle is that, let me say that trust is really fundamental to privacy. And so the goal of the fourth principle is that nobody should have to take privacy claims on blind faith. Ideally, everyone, all of the stakeholders should be able to verify and understand kind of the privacy approaches taken in a particular system. And I do think it's really useful to think about like a concrete cross-device FL system, for example, as we expand on another set of facets of privacy in particular. And one of the things that is nice about FL is it makes the different roles in a system much more explicit, because they're actually kind of often different physical locations, right? So you have FL users with devices where the data actually resides. You have maybe a data center that coordinates the FL processing and computes aggregates. You have an ML or data engineer working at their workstation that's asking the federated learning system to compute different statistics or train different models. They then would evaluate those models and then make a final decision about which trained model to, say, ship out to user devices. And what's nice about kind of isolating out or being explicit about these different parts of the workflow is it's then very natural to talk about adding a policy layer to this kind of system that controls what data is accessed, for what purpose, what information is allowed to flow across these different boundaries. So this is what gives us kind of a powerful set of tools to enact that first privacy principle, and ideally also to provide verifiability. I think we'll see a little bit later in the talk that this same kind of approach is actually very valuable for privacy sensitive centralized data as well. So the next thing I think to consider when talking about privacy is what threat models are you actually concerned about? And I think there's two main axes that kind of help define a threat model. The first is kind of what are the potential access points or attack surfaces of the system that you're worried about? This could be the client devices, the network, the server, the intermediate outputs that are materialized on the ML engineer's workstation, or kind of the final publicly released outputs like models that are shipped to all Android devices. And then for each of the active components of the system, we can think about whether those are treated as trusted from the point of view of privacy, honest but curious in that they can eavesdrop, but they don't influence the protocol, or are actually actively malicious and deviate from the protocol in ways that might compromise privacy. And so obviously the goal would be to provide as much privacy as possible, even if all aspects of the system were malicious, but that's a very high bar. So most of the privacy technologies we develop will only address some subset of these different threat models and are in service of some subset of the different privacy principles I mentioned. So fundamentally, federated learning and analytics are data minimization technologies. They encode principles like focused collection, ephemeral updates, immediate aggregation, and so on. So we want to minimize the copies of data that are kept in different parts of the system. We want to limit the collection of data or what's sent to the server to focus updates that are intended to improve a particular model or answer a particular query. We try to limit data lifetime and process data as early as possible, kind of boil it down to the essential bits as soon as possible. And then we minimize data retention through all stages of processing in a federated system. And so I think, you know, it's fairly easy to imagine a variety of threat models for these data minimization strategies would help mitigate privacy risks. Data anonymization is really complementary to FL. Data minimization doesn't address what can be learned from the actual outputs of the system, like the model parameters or statistics that we release. So the XKCD about language models kind of memorizing user data is a humorous example of this, but we of course have lots of research that shows that this is actually a real concern with modern real world models. So differential privacy is kind of the gold standard here. It provides a strong formal guarantee against a very powerful class of adversaries, and I'll say more about that in the next section of this talk. But I also wanted to give a big shout out to empirical privacy auditing techniques, which I think are really important and really complementary to formal differential privacy guarantees. Unlike kind of the formal guarantees, empirical privacy auditing can actually detect flaws in the implementations of anonymization techniques, and can also kind of more precisely calibrate the risk with respect to kind of more specific and less worst case threat models than the kind of very strong adversary that differential privacy essentially assumes. So a big thrust from our team and partner teams at Google over the past few years has been making differential privacy practical for federated learning. And of course, it's not quite clear that it's practical for even standard centralized machine learning yet either, so we've been working on that as well. I won't have time to dive into a lot of the technical details in the talk, but there's a couple of observations I wanted to highlight before I talk about some of our actual recent progress in using these techniques in production. The first thing that I think is sometimes underappreciated, at least in the research literature, is the importance of the unit of privacy in DP. So we don't need the formal definition of differential privacy for this talk, but a useful informal definition is that differential privacy says that when you change one X in the training data, the distribution of output models hardly changes, or changes in a quantified way. Writing the definition in this way makes it really clear that a really important component of the definition is what is X. Language models are an interesting example here because there's a lot of actual potential choices for X. You could imagine changing, for example, a single character or word in the training data and not wanting that to have too much influence on the model. I think it's fairly clear that that would be a very weak notion of privacy. The most widely used unit of privacy is probably example level differential privacy. That's the closest to kind of what standard ML infrastructure, what can be combined with standard ML infrastructure. But it's a bit of an odd notion when it comes to language models, because the example level DP there basically means the sequence of tokens that form a row in a batch. And so if you change your model parameters or how you pre-process data, kind of your unroll length, you're actually changing your unit of privacy. So this isn't necessarily a particularly meaningful semantic concept. So I think that the most useful semantic units of privacy for language models would be things like paragraph level DP, document level DP, user level DP, and so on. And conveniently, federated learning algorithms are very well suited to providing these multiple example notions of privacy, because they can kind of process all of the training examples from one unit together and therefore bound the influence of that whole set of examples on the overall model. So we focus in particular on user level privacy because I think that's often the most important notion, but I think the techniques extend to these other multi-example units of privacy as well. Another point that I think we've really come to appreciate is that the trade-off space in machine learning with differential privacy really has at least 4 dimensions. I think everybody is used to thinking about privacy versus accuracy trade-offs. You know, you add more noise in order to get a stronger privacy guarantee, and it degrades the accuracy of the model. That's pretty natural. But that's only true if you kind of fix your operating point on these other dimensions of computation cost and data set size. So for example, if you have a fixed data set size, you can add more noise but scale up your batch size accordingly, and often pay no cost in privacy, pay no cost in accuracy while arbitrarily increasing privacy. given that you're willing to throw enough computation at it, right? Scaling up even all the way to things like full batch gradient descent. So I think this often means, that the right questions to ask here are not things like, will DP work for my model, but things like, well, how big of a population do I need and how many clients per round would I need to process in order to achieve good privacy utility trade-offs? Or if you're going to fix the computation cost, how much noise can I add without degrading privacy? Because we strongly feel that getting any finite differential privacy guarantee is a big step forward from using completely non-DP training algorithms. So putting some of these observations together, along with some important algorithmic improvements, we were able to launch what we think was the first production neural network trained directly on user data and announced with a formal DP guarantee. So I think this is a really big milestone accomplished by collaborations across a bunch of teams at Google. In particular, this is a user-level differential privacy guarantee achieved versus federated learning, but I don't think it had even been done in the easier case of example-level DP with centralized training before this. So for more information on this launch, you can see our blog post, and there will also be a talk later in the workshop. So there's been some increasing interest in privacy for Gboard lately, so I wanted to take this opportunity to highlight some of the ongoing work we've been doing to strengthen the privacy protections used in our production FL applications, including Gboard. And I'll try to do this kind of in light of some of the privacy principles and threat models I was mentioning earlier. So in the spirit of improving data anonymization for the intermediate and final models that are released to model engineers and also published globally on Android devices, the DPFTRL algorithm is now used to train Gboard language models, including next word prediction and rescoring in over 5 languages. And we're on track to extend that to all languages in Gboard in 2023. To support stronger data minimization, preventing, say, an honest but curious server from accessing per user updates, we've continued to advance the state of the art with our secure aggregation protocol. Secure aggregation is now used in production for over 60,000 aggregations daily across all Google Federated Learning and Analytics workloads. And that includes production FL models trained for the Android system, as well as Gboard's key correction triggering model. So we've been experimenting with SecAg and Gboard for multiple years, and getting to this milestone has taken multiple iterations of infrastructure improvements as well as algorithmic improvements like subgraph SecAg. So this has been a long time in the works, and we're continuing to push SecAg forward to more and more applications. We're also interested in extending kind of the data anonymization guarantees, not just to kind of the models released to the model engineer or made public, but actually to an honest but curious server. So this would be the realm of distributed differential privacy. And so we've developed a clear path to combining secure aggregation with distributed differential privacy. So these are noise shares added on the client device, so that by the time the server sees the model update, it already has an appropriate amount of noise integrated into it for differential privacy. We're combining those techniques with some additional central DP noise, so that we'll have the strongest DP guarantee for the models released publicly, but we'll still have a finite differential privacy guarantee for an honest but curious server. And finally, in support of the principles of transparency and verifiability, Google's Federated Learning and Analytics client code is now open sourced on GitHub in the Federated Compute repository. And also Android Private Compute's Core's FL jobs are visible in a network log. You can learn more about that in the Private Compute Core white paper I've linked here. And as I said, I won't have time to really dive into these technical details. But we've been continuing to improve the DPFTRL algorithm by replacing tree aggregation with optimal matrix factorization-based DP mechanisms. So this slide is really just a teaser. I've included kind of the two matrices that define the optimal mechanism for a particular training instance here, because I think they're pretty cool looking. You can clearly see that these matrices were specifically optimized for 6 epochs of training, for example. So if you're interested in this, you can check out a couple of our papers, and there'll be more in a keynote talk from Augerdeep tomorrow in tomorrow's edition of the workshop. And he'll talk a little bit more about applications in Gboard as well. But in the spirit of time, I'll continue the tour. I wanted to mention a few updates with TensorFlow Federated. One of our big goals has been to continue to grow the TFF open source ecosystem. So we've launched a new special interest group on federated approaches that provides collaboration channels like a Discord server, as well as regular meetings. Some of the current members include the OpenMind open source community, LinkedIn, and Google, but of course more are definitely welcome. I just lost my slides here. Let me see if I can get them back. There we go. One of the first collaborations between OpenMind and TensorFlow Federated in this new TensorFlow Federated in this new collaboration builds on an idea I was mentioning earlier about how policy layers fit naturally into federated learning. So federated learning algorithms kind of naturally limit data access to specific focus computations that release aggregates. And we now know how to provide effective algorithms for user-level differential privacy. And those things are all very useful for centralized privacy-sensitive data as well. And so the idea of this collaboration is to build a platform that makes it easier to set up that kind of infrastructure. And there have been a bunch of expansions in just kind of the core functionality of TensorFlow Federated. Many new learning algorithms, general purpose optimizer APIs, baselines that make it really easy to kind of spin up your own research and compare to a lot of work from our group and other research groups. Support for training models defined not just in TensorFlow, something we're really excited about. TensorFlow Federated, despite the name, is really quite agnostic to the underlying modeling framework. And so we'd like to see the generality of TFF to continue to expand. So if this is something you're interested definitely reach out. And there's been also a lot of progress on the distributed runtimes, scaling up to tens of thousands of clients per round. This enables kind of the collaboration I talked about on the previous slide, as well as just making it much more efficient to do large-scale federated learning research. Federated Analytics is also increasingly important at Google. I don't have time to dive into a lot of the details here, but one public highlight I wanted to mention, again in the spirit of transparency and verifiability, is that some of the most useful federated analytics algorithms are now available in open source and TFF analytics. That includes private heavy hitters, that is frequent item discovery algorithms, based on secure aggregation and IBLTs, and that comes with central differential privacy, and algorithms for private quantiles that can be used with either central or distributed differential privacy. All right, with my last few minutes, because I do want to leave a few minutes for questions, is really starting to scratch the surface of this research question. This is something we've started to think about more seriously in the past year or so. Can we use federated learning to train models that are too big to fit on a mobile device? I think the motivation for this question is pretty clear, right? Large models, very large language models in particular, foundation models, have made enormous progress in machine learning recently. And here, large frequently means too big to fit on device. That's even for inference, even with compression techniques applied. So how do we do FL on these models, right? How can we benefit from these kind of models in a federated setting? There's a variety of approaches to this. One is to kind of combine centralized training with federated training. I think Sean is going to talk a little bit more about that in one of the mini workshops later in this workshop. But you know, a potential and I think very promising solution is to try to exploit data-dependent model sparsity. And with that in mind, we've developed this new primitive we're calling Federated Select. So what is this? It's a really basic idea, right? I don't want to oversell it, but I also think it's fairly useful to call this out as a precise primitive in federated computations. The basic idea is that clients can each generate their own set of keys, so think integer keys, based on processing their local data. So then those keys specify kind of what parts of the server value, the server model they want to be downloaded. So basically in standard federated learning, we think of a broadcast approach where all clients, where the server broadcasts the same global model to all of the clients. Here, each client can locally compute their own set of keys and download a different slice of the model. And this, of course, can be combined with a federated broadcast. This is a really useful primitive for a bunch of reasons. It's kind of simple enough that it's reasonable to expect production federated learning infrastructure to implement this kind of a primitive, but it also enables a wide array of different algorithmic approaches to exploiting sparsity. And it's also a primitive that is amenable to various privacy preserving implementations. In particular, federated select could be implemented using a private information retrieval technique that would prevent the server from learning which slices were downloaded by which clients. So I wanted to just give a couple of examples of how this could be used. One way to use this is even in a data independent way, where each client downloads essentially a random subset of the server model and only trains and updates that subset. So this has been called the Federated Dropout idea, and that fits very naturally into what's supported by this primitive. Maybe a more interesting one is embedding selection. So imagine a language model where the server had a vocabulary of 1 million words, but each client only had a relatively small amount of data. Then the server could broadcast kind of the core non-embedding parts of the model shown in blue here, but each of the client devices could only download the subset of the embeddings that were actually relevant to the local data set. That is the embeddings for the words that were actually in the training data on that particular device. And so this actually then becomes just a more efficient, a more efficient implementation of what you might do otherwise. And maybe the most interesting direction is to actually consider model architectures that have more complex notions of sparsity that could be exploited by federated select. So in particular, sparse mixture of experts, you can imagine kind of running the gating network which selects the relevant experts on device, using that to determine the keys for federated select, and making sure the client device only downloads the subset of expert parameters that are relevant for that device. So this is really just a teaser. There's some additional results in the white paper I mentioned, but I think I would say they're very promising but preliminary, and I think this is a very open direction for research, thinking about what's the right way to exploit sparsity in the federated setting. So I think I'll leave it there. I'll leave some links up, and maybe I'll try to put these into chat in a second to make it easier to find some of the papers and other announcements that I mentioned in this talk. So with that, let me just say thanks, and I think we'll maybe have a few minutes for questions. But if we run out of time here and you have questions, thoughts, or feedback, feel free to reach out to me directly as well. Thanks.
Thank you, Brendan. And we do have a question from Aurelian, who asks, for language models in particular, is user-level DP really enough? text data from a given user may contain information about other users. What can we do to address this?
Yeah, that's a great question, and I'm not sure we have a great answer yet. I think, you know, this is one of the reasons that I highlighted that different units of privacy might be relevant. Right? You could consider larger units of privacy, like a whole organization or whole groups of people. Obviously, the larger the units of privacy is, kind of the more noise you need to add, and achieving DP becomes more challenging. So I don't think right now there's a silver bullet answer to this question. I think you actually have to think carefully about the particular application and what notion of privacy is most meaningful there. Oh, and I see a chat from Florian that they have a paper that directly tackles this question, but I think it's still a hard question. Yeah.
Yeah, we have less than a minute left. Is there any further questions for Brendan? Okay. Awesome. Thank you so much.
I wasn't provocative enough. I'll try harder next time. But I think there'll be a panel as well, so you'll have more chances.
That's right. Great. Okay. Awesome. Thank you, Brendan.